In 2009, a shocking discovery was published in the prestigious scientific journal Nature, leaving the paleontological world in awe. At the Cerrejon coal mine in northern Colombia, a team led by Dr. Jason Head unearthed dozens of fossilized vertebrae and ribs. After careful analysis, they determined that these were the remains of a previously unknown species of ancient snake, the largest snake that ever lived on Earth. Based on the size of the vertebrae found, similar in structure to modern pythons but many times larger, scientists estimated that the creature could have been up to 13 meters long, which was later revised to 14.3 meters when the skull was analyzed. Its body weight was around 135 kilograms, equivalent to that of an adult giraffe. The giant snake was named Titanoboa cerrejonensis, with Titanoboa meaning giant python and cerrejonensis being the name of the place where it was discovered. Compared to the largest snake in existence, the green anaconda, Titanoboa dwarfs it in both length and weight. Even more astonishingly, its size was comparable to some carnivorous dinosaurs, causing scientists to question its ability to survive and its post-dinosaur habitat. Around 58 to 60 million years ago, shortly after the dinosaurs went extinct at the end of the Cretaceous, Earth entered the Paleocene period, the first stage of the Cenozoic. This was when Titanoboa cerrejonensis, the largest snake ever to have lived, emerged and flourished. Interestingly, Titanoboa was not the only giant creature at the time. Fossils found in the same geological strata at the Cerrejón coal mine in northern Colombia have revealed a vivid picture of a diverse ecosystem where giant reptiles coexisted in a warm coastal mangrove environment. Among the fossils excavated in this area, in addition to Titanoboa, there are giant turtles such as Carbonomys cophrenia, with a shell length of up to 1.8 meters, and the ancient crocodile Acherontissuchus guajirayensis, a freshwater crocodile that was about the size of today's crocodiles. Also, in this fossil layer, scientists found fossil specimens of plants typical of the tropics such as palm trees, giant ferns, and woody plants of the legume family, species that need a hot and humid climate to grow. This clearly shows that this area was once a dense, nutrient-rich tropical forest with a dense network of rivers, an ideal environment for the development of giant cold-blooded reptiles like Titanoboa. One of the factors that determined the existence and development of Titanoboa was the environmental temperature. As a cold-blooded animal, Titanoboa relied entirely on external temperatures to regulate its metabolism. Researchers analyzing carbon isotopic compositions in fossilized plants and marine sediments near the Cerrejon site have estimated that the average temperature at the time was between 28 to 30 °C, significantly higher than today's average temperatures. This is the optimal temperature to sustain the metabolism of a giant creature like Titanoboa. With a warm climate, dense forests, and abundant food sources, the snake could have grown to a size far exceeding that of modern snakes. In addition, the Paleocene Cerrejon site is identified as one of the world's oldest fossilized rainforests. Analysis of the stratigraphy and ancient vegetation suggests that the ecosystem was very similar to today's Amazon rainforest, but much warmer. This is evidence that the hot and humid climate not only promoted biodiversity, but also provided ideal conditions for the formation of giant animals. Abundant biological resources, such as large freshwater fish turtles and other aquatic animals, also served as a rich food source, helping Titanoboa grow to its extraordinary size. In short, Titanoboa was not just the result of a single evolution, but the product of a special ecosystem. A hot climate, high humidity, dense tropical forests, and rich flora and fauna. These factors combine to create an ideal habitat for giant snakes to dominate the post-dinosaur ecosystem. Therefore, studying the habitat of Titanoboa not only helps to better understand this snake, but also provides a comprehensive view of the Earth's ecosystem in the early Tertiary period. One of the most hotly debated questions about Titanoboa is what allowed this snake to grow to such a huge size. To date, there have been two main hypotheses proposed to explain this remarkable evolutionary phenomenon: the influence of tropical climate and the lack of competition from other predators. Hypothesis 1: high environmental temperatures promote size growth in cold-blooded animals. Titanoboa is an ectothermic reptile, meaning its body does not generate its own heat but depends on the environmental temperature to maintain its life activities. Scientists have studied the relationship between temperature and body size of modern snakes, including the South American green anaconda. Accordingly, an anaconda living in an environment with an average temperature of about 27 degrees water usually only grows to a maximum of about 6 meters. Based on the corresponding physiological formula, the research team led by Dr. Jason Head estimated that for a snake to reach a length of more than 13 meters like Titanoboa, its habitat would have needed to be at least 30 to 33 degrees C. Studying sediments and plant fossils at the Cerrejon mine, where Titanoboa was found, shows that the area was once a hot and humid tropical climate with temperatures ranging from 28 to 30 degrees and atmospheric CO2 concentrations about 50% higher than today. This provides strong evidence that this particular climate was the ecological factor that drove Titanoboa's giant size. Its large body not only helped it hunt larger prey, but also maintained its body temperature efficiently in tropical conditions, a significant evolutionary advantage. Hypothesis 2: the absence of competition from mammalian predators. After the extinction of the dinosaurs at the end of the Cretaceous Earth entered a period of ecological reestablishment. During the Paleocene, modern carnivores had not yet fully evolved or were small in size. This created an ecological vacuum, that is, a lack of predators competing for living space and food resources. Titanoboa and other large reptiles, such as ancient crocodiles and giant turtles, took advantage of this opportunity to dominate the food chain. Some scientists, notably climatologist Kevin Padian and biologist Kay Snyderman, argue that in a low-competition environment without the presence of large predators, Titanoboa was not under pressure to survive from natural enemies. This allowed it to consume abundant food resources and grow to the maximum size that the environment allowed. This is also a common phenomenon in evolution called maximum size in low-competition environments. However, these two hypotheses are not necessarily mutually exclusive. In fact, most scientists agree that Titanoboa was able to become gigantic as a result of a combination of factors including a warm climate that facilitated metabolism and a lack of competition that paved the way for it to occupy the highest ecological niche in the food chain. The ideal environment combined with the unique ecological conditions created an evolutionary golden opportunity for Titanoboa, a snake that was probably the nightmare of every living creature living in the ancient mangroves of Colombia. One of the biggest mysteries about Titanoboa is not just its enormous size, but how it lived and hunted. To answer this question, paleontologists have carefully analyzed Titanoboa's teeth-jaw structure and body features, and these findings offer a completely different view from the popular image of a monster snake that devoured crocodiles or land animals. The first thing to note is that Titanoboa's jaw structure was not well suited to hunting on land. While most large predatory snakes like modern pythons or anacondas have teeth that are firmly attached to the jawbone, helping to hold on to prey when squeezed, Titanoboa's teeth were loosely attached and flexible, a structure similar to that of modern fish-eating snakes like the brown water snake. In addition, Titanoboa's teeth are thought to be larger than those of a typical snake, with the teeth being thin and slightly curved inwards, ideal for capturing slippery fish underwater. The second clue that supports the hypothesis that Titanoboa lived primarily in water is its body morphology. Its vertebrae show a flattened structure which allowed it to move flexibly in a semi-aquatic environment similar to modern water snakes. This allowed Titanoboa to easily hide on the river bottom, ready to ambush its prey, mainly large fish, from close range. With its superior size, this snake did not need to chase its prey, but simply waited for the right moment to strike. Another unique feature is that Titanoboa's habitat, the ancient mangrove and lake areas of Carayon, had an extremely rich aquatic fauna. Fossils found here show the presence of many large freshwater fish, including ancient cartilaginous and bony fish, and even catfish up to several meters long. This is the ideal food source for a giant fish-eating snake like Titanoboa. Despite once ruling the rivers of the Paleocene, Titanoboa cerrejonensis didn't survive long. Paleontologists have determined that the giant snake disappeared within a few million years of its appearance, a short time by geological standards. So what led to Titanoboa's extinction? The answer lies in global climate change, which is crucial to the survival of cold-blooded animals like Titanoboa. Titanoboa thrived in an environment with average temperatures of around 28 to 33 degrees, the ideal temperature for the giant reptile's metabolism. However, around 56 million years ago, Earth entered a period of major climate change known as the Paleocene-Eocene thermal maximum (PETM), followed by a period of prolonged cooling. After the thermal peak, global temperatures dropped significantly, due to natural climate change Earth orbital cycles and a drop in atmospheric CO2 concentrations. In the Cerrejon region, where Titanoboa once lived, average temperatures dropped below the threshold needed to maintain its enormous size. As a cold-blooded animal, Titanoboa was completely dependent on ambient temperatures to survive. As temperatures dropped, its metabolism slowed, reducing its digestion rate, limiting its ability to hunt, and even making it vulnerable to disease. Its large size was an advantage in hot climates, but became a liability when temperatures dropped. Unable to adapt to climate change, Titanoboa was gradually pushed to the brink of extinction. In addition, the emergence and development of carnivorous mammals also contributed to changing the ecological balance. During the Paleocene to Eocene transition, carnivores began to evolve faster, with more thermoregulation and more flexible hunting strategies. This created new competitive pressures in the food chain. Although there is no direct evidence that carnivores killed off Titanoboa, the loss of its dominant position in the ecosystem certainly had a major impact on the survival of this giant snake. In short, the cause of Titanoboa's extinction was a combination of climate change and changes in ecological structure. When the environment could no longer maintain ideal temperatures and competitors began to appear, the snake that had been a symbol of post-dinosaur power could not survive. The disappearance of Titanoboa is a clear demonstration of the law of evolution, that even the most giant creatures cannot withstand the forces of nature and time. The question that seems like it only exists in science fiction movies is being seriously raised by some scientists. Can Titanoboa, the giant snake that once dominated ancient tropical forests, reappear in the future if conditions are right? The answer is not necessarily impossible, because the existence of Titanoboa in the past was a direct result of its habitat, especially the climate and ecological structure. For Titanoboa to survive again, the first and mandatory condition is that global temperatures must increase significantly. As mentioned, this snake species can only thrive in temperatures ranging from 30 to 33 degrees C. In the current context, climate change is making many areas on Earth, especially equatorial regions such as the Amazon, hotter and wetter than ever. The average global temperature has risen by more than 4 degrees C since pre-industrial times, and if this trend continues, subtropical regions could approach the temperature range that supported Titanoboa in the past. Temperature is only part of the problem, however. A giant snake like Titanoboa needs a rich food source, especially large fish and aquatic organisms, as well as a large undisturbed semi-aquatic environment. With the rapid destruction of the Amazon rainforest by logging agriculture and urbanization, this ecosystem is severely shrinking. Even if the climate gets warmer, if the habitat can no longer support a diverse and stable food chain, the chances of a species like Titanoboa re-evolving are virtually nil. Another factor to consider is evolutionary pressure. Titanoboa did not become huge by accident. It was the result of millions of years of genetic mutation and natural selection in a very special ecosystem with little competition from predatory mammals. Meanwhile, mammalian predators have now taken over almost all the dominant positions in the food chain. Modern snakes, even large ones like pythons and anacondas, no longer have a survival advantage by evolving to be larger because it would require more food, be easier to detect, and have a harder time moving around in an ecosystem that has been significantly reduced by humans. Genetically, there is also no indication that modern snakes are evolving to increase in size. There is no fossil evidence that any species is continuing the lineage of Titanoboa in the true sense. Although they are both in the Boidae family, the family of snakes modern snakes have adapted in markedly different ways. In short while, it is theoretically possible for Titanoboa to return if the right climatic and ecological conditions are met in practice. This is highly unlikely. Not only is the Earth changing in ways that are not conducive to cold-blooded giants, but the evolutionary structures and habitats that once gave rise to Titanoboa no longer exist. The return of a modern Titanoboa, if it ever does, would not be a simple resurrection, but the result of an entirely new, long-term, and unpredictable evolutionary process. Leave your thoughts in the comments below. We'd love to hear what you think of this scenario. Don't forget to share the video if you find it interesting, and click subscribe to Cosmic Y so you don't miss out on any more exciting scientific discoveries. See you in the next videos.